Episode 3. Tharsis, the bulge that reshaped Mars. How could something raise such an enormous part of a planet? In the last episode, we took a tour of Mars from orbit. We saw a planet divided between ancient southern highlands and lower northern plains. We saw Hellas, one of the largest impact basins in the solar system. We saw Valles Marineris cutting thousands of kilometers across the surface. And we saw the largest volcano in the solar system, Olympus Mons. But several of those features have something in common. Their stories lead us back to one enormous region of Mars, Tharsis. At first glance, Tharsis doesn't look as dramatic as Olympus Mons or Valles Marineris. It isn't a single mountain. It isn't a crater, and it isn't a canyon. Instead, an enormous portion of the Martian surface has simply been raised upward. So the question for this episode is, how could something lift such a huge part of a planet? Let's look at the evidence. A rise on a planetary scale. The best way to understand Tharsis is from a topographic map. On a MOLA elevation map of Mars, elevation is represented by color. The lower northern plains appear in blues and greens. Much of the southern highlands appears in yellows and oranges. And then, in the western equatorial region, something remarkable appears. A huge area of high terrain. This is the Tharsis Rise. It stretches thousands of kilometers across Mars, and parts of it rise several kilometers above the planet's average elevation. But sitting on top of this already elevated terrain are some of the largest volcanoes on Mars. Olympus Mons lies along its western edge, and crossing the central Tharsis region are three enormous shield volcanoes: Ascraeus Mons, Pavonis Mons, Arzia Mons. Together, they're known as the Tharsis Montes. These volcanoes are spectacular. But they're only the most visible part of a much larger story. Because the real geological feature here isn't simply the volcanoes. It's the enormous rise beneath them. What could build something this large? Tharsis is fundamentally a volcanic province. Over immense spans of Martian history, magma rose from deep within the planet, and enormous quantities of lava reached the surface. Layer after layer, eruption after eruption. The accumulated volcanic material added an extraordinary amount of mass to this part of Mars. But simply piling lava onto the surface isn't enough to explain everything we see. Scientists think the story also involves processes deep inside the Martian interior. Hot material rising within the mantle could have pushed upward on the crust while supplying magma to the volcanoes above. The result was not simply a collection of volcanoes, it was a vast region of elevated crust, a volcanic and tectonic province on a planetary scale. And Tharsis didn't appear overnight. Its development extended across an enormous portion of Martian geological history. That becomes important, because when you build something this large on the surface of a planet, the rest of the planet responds. Imagine the weight. Think about what was happening. An immense amount of volcanic rock was accumulating in one region. At the same time, forces from within Mars were helping raise the surface. That creates stresses in the crust, and we can see evidence of those stresses today. Look closely at maps surrounding Tharsis, and you'll find enormous systems of fractures, faults, and grabens extending across the landscape. Some appear to radiate outward from the Tharsis region. Others form vast tectonic structures around it. The crust of Mars was being stretched, fractured, and deformed. Which brings us to something we saw in Episode 2. Travel east from Tharsis, and you encounter one of the most extraordinary geological structures in the solar system. Valles Marineris. The Tharsis-Valles Marineris connection. Valles Marineris stretches roughly 4,000 kilometers across Mars. If we simply looked at photographs of it, we might assume we're looking at an enormous river canyon, but its position next to Tharsis provides an important clue. As Tharsis developed, enormous stresses affected the surrounding Martian crust. The crust stretched, faults developed, and large blocks of terrain dropped downward. That tectonic activity appears to have played a major role in creating the original structure that eventually became Valles Marineris. Later, landslides, erosion, and possibly flowing water modified parts of the canyon system. But the initial story probably wasn't a river carving downward from the surface. It was the crust itself pulling apart. So when we look at Valles Marineris, we may actually be looking at one of the consequences of the formation of Tharsis. That's why understanding Tharsis comes first. But Tharsis created another mystery. Why are the volcanoes so enormous? Earth has enormous volcanoes, but nothing quite like the giants of Tharsis. And one reason may be a fundamental difference between Earth and Mars. Plate tectonics. On Earth, the crust is divided into moving tectonic plates. A plate can slowly move across a relatively stationary source of magma below. The Hawaiian Islands provide a familiar example. As the Pacific Plate moved across a volcanic hotspot, new volcanoes formed one after another. That's why Hawaii forms a chain. Mars appears to work differently. Mars does not have Earth-like plate tectonics operating today, and there is no clear evidence that its crust ever behaved exactly like Earth's modern system of moving plates. That means a volcanic source could remain beneath approximately the same area for an extraordinarily long time. Instead of creating a long chain of volcanoes as the crust moved overhead, repeated eruptions could continue adding material to the same enormous volcanic structure. And nowhere is that more dramatic than Olympus Mons. But Olympus Mons deserves its own episode, because there's another consequence of Tharsis that may be even more remarkable. Could Tharsis have changed the entire planet? When you redistribute enough mass on a planet, you can potentially affect much more than the local landscape. Scientists have investigated whether the enormous mass associated with Tharsis could have changed the orientation of the Martian crust relative to the planet's rotational axis. The idea is known as true polar wander. This doesn't mean Mars suddenly flipped over. Instead, over geological time, the outer portion of a planet can shift relative to its spin axis as mass becomes redistributed. And Tharsis represents an extraordinary concentration of mass. How much Mars actually reoriented, and exactly when, remains an active area of research. But the possibility illustrates just how significant Tharsis is. We're not talking about an isolated volcanic field. We're talking about a geological province large enough to potentially influence the structure and orientation of a planet. Tharsis and ancient Mars. There's another reason Tharsis matters: timing. Mars was changing dramatically while Tharsis was developing. Ancient river valleys were forming. Water was flowing across portions of the surface. The atmosphere was evolving, and enormous amounts of volcanic material were being erupted. Volcanoes don't release only lava. They also release gases. On Earth, volcanic eruptions can release water vapor, carbon dioxide, sulfur compounds, and other gases from the planet's interior. Martian volcanism would also have transferred gases from inside Mars into its atmosphere. That means Tharsis may have played a role in the evolution of the Martian atmosphere and climate. Exactly how large that role was is much harder to determine. And this is where we have to separate what we can observe from what we infer. Let's look at the evidence. What do we observe? We observe an enormous elevated region thousands of kilometers across. We observe some of the largest volcanoes in the solar system sitting on and around it. We observe immense lava flows and volcanic terrain, and we observe enormous systems of faults and fractures associated with the region. What do scientists strongly infer? Tharsis was built through immense volcanic activity, combined with processes occurring within the Martian interior. Its development placed enormous stresses on the crust, and those stresses are closely connected with tectonic features surrounding Tharsis, including the development of valles marineris. What is less certain? Exactly how the mantle beneath Tharsis behaved through time, how volcanism evolved over billions of years, how much Tharsis contributed to changes in Mars's atmosphere and climate, and how significantly its enormous mass may have reoriented the planet's crust. Those are much harder questions, but that's also what makes Tharsis so interesting. The bigger picture. Go back to our map of Mars. Now Tharsis looks different. It isn't simply the place where several giant volcanoes happen to sit. It's one of the great organizing features of Martian geology. Volcanism built an enormous province. The crust rose and deformed. Fault systems spread across huge distances. And immediately beside it, the surface fractured to help create valles marineris. Tharsis may even have influenced Mars on a truly planetary scale. And sitting above all of this is the most spectacular product of Martian volcanism. Olympus Mons. It's so wide that if you could stand on its lower slopes, you might not even realize you were standing on a mountain. Much of the volcano would disappear beyond the horizon. So how did Mars build a volcano that large? And why didn't Earth? That's where we're going next. I'm the Mars Explorer. I'll see you in the next episode.